Hello guys. Now we start with the course on statistical learning theory. It is completely based on our book, a book by Moacir Antonelli Ponti and myself, Rodrigo Fernandes de Mello. This book is entitled Machine Learning: A Practical Approach on the Statistical Learning Theory by Springer. You guys can find more information on the book on the Springer's website. As I mentioned before, my name is Rodrigo Fernandes de Mello. I am associate professor with the University of São Paulo, Brazil. This is my website and this is my email. So if you guys have questions and any kind of doubts, you can send me by email or we can discuss during the virtual office hours, as I will mention later. So this course has the objective of introducing the theoretical foundations on supervised learning, the basics of supervised learning theory, I would say so. So it's basically devoted to bring some answers on the complexity of algorithm biases, on subjects such as the minimal sample size necessary to ensure learning, how we can, or what kind of tools or theoretical tools we can use to ensure learning as well. And in addition, we're going to discuss some things like SVMs, like support vector machines and kernels and things like that. So subjects include what and how to define the algorithm bias, how to formulate supervised learning. This means how we can prove supervised learning works, or let's say indeed learns, and not just happens by chance. That's quite important. So a result is not just a classifier is not just providing some output out of the blue, but actually it is producing some sort of generalization from data. We're going to discuss that in detail, of course. And how to prove a supervised learning algorithm learns, as I mentioned. We are going to talk about the empirical risk minimization principle by Vapnik. This Russian guy that devoted 35 years or more of his career to come up with theoretical proofs for supervised learning. We're going to discuss also and talk about Chernoff and Hofstad's bounds to come up with upper bounds, probability upper bounds for learning guarantees. We are also discussing this course on the Vapnik-Chervonex dimension, which is a capacity measure to understand biases, algorithm biases, how relaxed or restricted some biases, and which are the effects of that particular space of admissible functions, as we're going to discuss later. We also talk about the sheltering coefficient, which is one of the most important subjects related to the statistical learning theory. It helps us to define the algorithm bias size, so we can understand if an algorithm has the potential of overfitting data or maybe underfitting a given or data as the sample size increases, as the sample size tends to infinity. We're also going to talk about support vector machines, which are in fact the best supervised learning algorithms. But that is the case only if we have the best feature space. So this means that maybe if you don't have the best feature space, the best as possible to provide to SVM, the result is not going to be that good. The result is going to be really poor in most practical scenarios. In that matter, we also discuss on the large margin bound, which is a theoretical formulation of algorithm bias complexity in terms of how the positive, let's say, positive instances are far from the negative instances in a given space, in a given data space. We also discuss on the algebraic formulation of the support vector machine classification problem and how to solve it. So from that we can implement, and we are going to implement, the support vector machine. What's going to bring like lots of theoretical stuff into play and practical stuff as well into play. Afterwards, we're going to analyze kernel transformations. We'll discuss about the linear and polynomial kernel effects on data spaces and also estimate their complexities, those space complexities, what's really interesting. Those are the references in this course. The first one is the book I mentioned, our book by Moacir Ponte and myself, Rodrigo Melo, which is entitled Machine Learning: A Practical Approach on the Statistical Learning Theory by Springer, August 2018. We also have this paper by Luxburg and Shokov, which is entitled Statistical Learning Theory, Models, Concepts, and Results. This is a very important paper to start with. I really recommend you guys to start reading this paper, and then you can go to the other documents. Okay. This is the basic book by Vapnik on the statistical learning theory. Okay. We also have another book by Shokov and Smola on learning with kernels, which is very interesting, quite important for the area. It brings like relevant discussions on support vector machine, theoretical proofs, regularization, optimization, and other stuff. Of course, it brings like so much in a single book that it makes, let's say, dense, and somehow it misses some points. It misses, it does not open up all those points related to optimization, regularization, and of course all other subjects. So it condenses most of the subjects, I would say so. This book by Bishop, it is really important as a machine learning review. So it brings the basic stuff of machine learning. I really recommend you, if you don't have a strong foundation on machine learning. This book by Boyd and Vanderberg is going to be used especially when talking about convex optimization, a subject that's going to come later, of course, later in this course. This one by Bazara and Jarvis and Shirali is related to linear programming or linear optimization. This is going to bring the basic linear optimization concepts to start with the development of the support vector machine. This book by Gilbert Strang, Introduction to Linear Algebra, has all the foundation for linear algebra, which is really interesting and really necessary to deal with machine learning. Some people think that calculus is more important. Of course, calculus is really important to tackle, to address machine learning problems. But at the end, without linear algebra, you have like no idea what's happening behind the scenes. The assessment is going to consider a project. So we're going to have single individual projects. Okay, so each person is going to deliver his or her project, And this project must include the theoretical and some practical evaluations. So for example, let's say someone wishes to analyze the bias of different learning algorithms. For example, I wish to analyze the bias for a given convolutional neural network architecture. So I just define the architecture and work on that particular architecture, only that one. And then I want to understand what's like the best, the minimum sample size to ensure learning given some confidence level, some probabilistic confidence level, things like that. And then I go for the experiments to show that that's the case, that indeed happens. So the important dates in that case are, I hope you guys deliver the project proposal in a single page. I mean, it's going to be an IEEE latex package. So a single page following the IEEE latex package, proposing the project on September the 18th, 2020, of course. And then you guys are going to deliver some reports, some development reports. Those reports must show what you did, which are the results you've got during along the project, along the development, and those are the dates. Those reports also have like just a single page. Okay, at the end, you guys deliver a final paper with the results, theoretical and practical results, bringing some project description, motivation, gaps, related work, and of course your contributions. That's going to be a 4-page paper only, okay? Also using the IEEE latex package. That deadline is December the 18th. And about the virtual office hours, I'll be available every Friday from 8:30 to 11:30. I will send you later through TDIA, which is our software, the software we're going to use, the TDIA web system. I send you guys a virtual room in Google Meet, and then we have the opportunity to talk and to discuss, and of course answer questions and look for some common grounds. This is my email, okay? And then that's all for this opening, okay? See you guys in the next module.